Welcome to the latest episode of Star Cells and God. This is the show where we explore some of the discoveries that are happening at the frontiers of science and describe how those discoveries provide evidence for God's existence, God's nature, and the reliability of Scripture. My name is Rana. I am a biochemist and a Christian apologist, and I work for an organization named Reasons to Believe. If you want to know more about Reasons to Believe, go to our website, www.reasons.org. Also, you can follow us on social media, RTB_official. And then, of course, please go to our YouTube channel, Reasons to Believe, and subscribe. There you can gain access to some great video content exploring a wide range of science faith issues. And then also use the notification button so that you are reminded the next time a new episode of Star Cells and God drops. I'm joined in studio by Dr. Hugh Ross, who is an astronomer, a Christian apologist, and the founder of Reasons to Believe. And the two of us are going to be talking about a couple of new discoveries that, again, have implications for the Christian faith. So, Hugh, I'll invite you to go ahead and lead off today.
Well, Fuzz, this is about a paper published in Nature a month ago, and it's about the moon forming event, and there's been tons of papers published about how the solar system began with 5 rocky planets and how Theia and the proto-Earth collided with one another and how that formed the moon and made the Earth a little bit bigger. And but what this paper is pointing out is that, we're quite confident that this is the story of how the moon formed, because you can't get the moon to form any other way than through the collision of 2 rocky planets, where one rocky planet is about twice the mass of Mars, and then you got Earth, the proto-Earth, slightly less than what Earth is today. And we have very detailed models that show that, hey, this explains the moon's mass, its orbit, its constituents. So there's a lot of confidence that this model is correct. But what they're pointing out in the paper, we have no direct evidence of Theia itself. Not surprising. I mean, if it collided with the Earth and merged with the Earth, I mean, that's going to be quite devastating to the planet Theia. And so what the paper is pointing out is the claim that they have the first direct evidence of Theia. So, and as I read it, I said, well, actually, I think there's other direct evidences that they've overlooked, but I'll focus first on what they're talking about. And let's show the first slide, which basically is an artist's conception of what the collision looks like. So you got these 2 rocky planets, and one's smaller than the other. And it's not quite as dramatic as what this NASA artist image shows, because at that time, the proto-Earth had an ocean thousands of kilometers deep. And so I kind of like the term merger, because that very thick ocean cushioned the collision. And so what happened is most of Theia got absorbed into the interior of the Earth, but there was a lot of debris. I mean, it wasn't as nearly as dramatic as this, but it's dramatic enough. A debris cloud formed around the merged 2 planets, and that coalesced to form the moon. And the composition of the moon is very similar to the composition of the present-day Earth, especially the surface material. So, again, very strong. And I've written about this evidence in my book, Improbable Planet. There's an update and design to the core. But I do like what this paper is saying is we have found direct evidence of the existence of Theia. And if I could get the next slide, which shows the interior of the Earth, and a little bit exaggerated because the crust and the asthenosphere aren't quite as thick as what you see, but they're trying to let you see it. But it is relatively accurate. You got the solid inner core, then you got the liquid outer core, that's that yellow part, and then you got the mantle. And the mantle has several layers. There's 2 predominant layers, and what they've been discovered decades ago is there's 2 huge blobs at the bottom of Earth's mantle, or on the top of the liquid core. And they're several thousand kilometers long. So they're not tiny blobs.
Right. And so they can get this information by
Size
seismology then.
Seismology, yes. So we've known about these two big blobs for some time. The latest, and they're not very thick, but they're smashed right against the top of the liquid core. But their cross-section literally is thousands of kilometers. So they're fairly big. But the latest seismology is telling us that these two blobs have a density that's about 2.5 to 3% greater than the deep mantle. And so this high density stuff. So what these dozen astrophysicists did is they did a computer simulation. How do we explain these extra dense big blobs at the bottom of the mantle? And they discovered the only way you can get an explanation is if indeed a merger event happened between two rocky planets. So those two big blobs at the bottom of the mantle, they're the remnants of Theia. So that's, they said, hey, we got direct evidence. It's been sitting there for 4.5 billion years. And their model actually showed that it indeed would be stable, that this collision event between Theia and the proto-Earth, you would get these big blobs at the bottom of Earth's mantle, and indeed they would remain stable. The key piece of evidence is that they're denser than we see in the rest of the mantle.
Now, is there any way you could get any compositional information about the blobs that are there then?
Well, they're thinking, and because you're using seismology, you can't go down like a chemist and make a sample measurement.
But I guess on density, you could do some kind of modeling to predict maybe what would be the likely chemical composition or elemental composition that would give you that
Well,
density.
here's the problem. The seismology is telling you that they're denser than the deep mantle by 1.75% to about 3.5%. So there's a significant error bar there.
Right.
I mean, what you're asking for, we're going to need a more accurate measurement of their overdensity.
And it's also something that wouldn't be soluble in the material of the mantle then either, right?
No. Well, what they do say in the paper is probably these two huge blobs are underdense in light elements. Because what's happening in the interior of the Earth, like even in the inner core, there's some oxygen, some hydrogen, some sulfur, and that gets squeezed out of the solid core, it goes into the liquid core, and then it diffuses out into the mantle. And so these two big blobs, and again, we're not certain, but it looks like they're underdense in those things, so they may be actually blocking the flow of these light elements out. So, but again, the error bars are fairly big.
Right.
So, but that's the thinking, is that they're probably don't have as many of these light elements as what we see in the rest of the deep mantle. Now, having read the paper, I'm saying, well, wait a minute. This is really good direct evidence, but we have other pieces of direct evidence. And one is what I call the density anomaly of planet Earth. And, the principle of rocky planet formation is that the closer the rocky planet is to its host star, the more heat it gets exposed to from the host star. And what does that heat do? It drives off the volatile elements.
Right.
So it drives off the hydrogen, the carbon, oxygen, nitrogen, drives off the water, and that causes the density of it to go up. And so the farther away you are from the host star, the less dense you'd expect the rocky planet to be. We see that in extrasolar rocky planets. It obeys that rule. We see it in our solar system with the exception of planet Earth. In other words, we see Mercury is about 5.5 grams per centimeter. Venus is about 5.1. You go out to Mars, it's I think it's like 3.95. And so we actually see, and you can calculate this fairly easily, that there's a relationship between the distance from the host star and the density of the rocky planet. And Mercury, Venus, and Mars obey that. Now, the one caveat is that they're still way denser than rocky planets orbiting other stars. But we have a good explanation for that. The sun transferred a lot of refractory elements and a lot of angular momentum to its rocky planets, more so by a huge margin than any other planet-star system that we've been able to observe. But we do see Mercury, Venus, and Mars obeying that density relationship. Earth does not.
Okay.
It's the anomaly. In fact, Earth is denser than Mercury, which is amazing because we're about 3 times farther away from the sun than Mercury, and yet Earth is denser than Mercury. How do you explain that extra density? Well, the merger event is really the only way you can explain that enhanced density.
Yeah.
So that would actually qualify as a second piece of direct evidence, because when you got, the Theia merging with the planet Earth, the light element material, the volatile stuff, gets dissipated interplanetary space, but the heavy stuff
Right.
gets sucked into the Earth. So you'd expect the Earth to be extra dense if it did indeed have a major collision event with a big rocky planet, at least one bigger than Mars. And then the third piece of evidence, if I could have the next slide, is we look at the Earth's crust and we see it's extra dense in heavy elements. And the heavier the elements, the greater the disparity in the extra density. And so what you see here is the quantity of certain heavy elements relative to what we would anticipate for a rocky planet the size of the Earth somewhere else in our Milky Way galaxy or somewhere else in the universe. And you can see that some of the density disparities are really quite high. And I put this in order. So we have 21 times as much copper as what you'd expect if Earth had formed, like Mars and Venus and Mercury had formed. And we have 50 times as much yttrium, potassium, lead, uranium, and thorium. You get down to uranium and thorium, you can see a huge overabundance. Also lead, 170 times more. Not surprising because lead is the daughter product of the decay of uranium and thorium. So if you got a huge abundance of uranium thorium, like you see in this chart, 610 times as much thorium, 340 times as much uranium, you'd expect you'd also get a huge overabundance of lead, 170 times. What's interesting is you look at potassium and copper, those are what I put VP beside them, which means they're vital poisons. Too much in your body, it'll kill you. Too little in your body, it'll also kill you. They have to be at just right levels. And so like potassium is a major component of all animals. A lot of potassium in your body and my body. But we live on a planet where we have 90 times as much potassium available to us. And so this is one reason why life is abundant on planet Earth. It's got the potassium abundance to support it. With copper, it's a factor of 21. I put yttrium in there. It's a heavy element, 50 times as abundant as what you'd expect elsewhere. And most people have not heard of yttrium, but it's really the go-to element if you want superconducting technology, because it really lowers the temperature in which you can get superconducting. And yet, look at all. So it's a rare earth, but we got 50 times as much of it as you'd expect elsewhere. So this, too, I would argue, is evidence. How do you explain this huge superabundance? Well, if you've got a collision between Theia and the proto-Earth, that would explain why we're so. And as you can see, the anomaly is enormous. It's not just a factor of 2. It's a factor of 90 times, 170 times, even 610 times. So we got 3 direct evidences for Theia, which means, hey, we really do have a good handle on the moon. And, thanks to the moon, again, we can have advanced life on planet Earth.
Right.
So it's kind of a nice little addition to what we've already got at reasons to believe on the moon forming event.
Yeah, I mean, to me, the moon forming event is one of those pieces of evidence for Earth design that I think a lot of people can really appreciate. Number one, it's the model for the formation of the moon is quite, as you mentioned, quite dramatic, and it's something that people latch onto, they remember. But just all of the things that the moon does to support advanced life on Earth is remarkable. And to think that you have to have a just right collision with bodies of the just right size, the just right angle of incidence, that's a bit eerie, I guess.
It is a bit eerie, and scientists who are studying the moon forming event and all the design that the moon reveals that makes advanced life possible on Earth, even the atheists among them are astounded by what they're researching.
Yeah.
I mean, I quote Tim Elliott in Improbable Planet, where he says, this is really causing us philosophical disquiet.
Yeah.
Because of the implications that it has theologically.
Well, one of the things that we do here at Reasons to Believe, of course, thanks to your leadership, is that we look at the case from science for the Christian faith through a creation model approach, where we make predictions about future scientific discoveries. So I'm just curious, do you think that eventually we're going to discover that the remnants of Theia in the Earth's inner mantle, outer core, is actually a design feature of the Earth, that it actually may be discovered to contribute to the capacity of Earth to support life?
I don't know about those two blobs in particular. I mean, without those, you would expect those blobs to be there if there is a moon forming event. And no question, we need the moon to be exactly as it is,
right,
to the exact history that it does. And even just for the Earth to retain its water and atmosphere, let alone its capacity to support life.
Yeah.
So that in itself, I think, is a remarkable indication of the handiwork of God, just the mere existence of those two blobs. It does explain an anomaly that's been mystifying, geophysicists for some time, is that the Earth's rotation axis, it wobbles a little bit. And so they've been thinking, well, maybe the oblate feature of the Earth. I'm wondering if these two blobs we're going to eventually find, hey, there's an extra density there, and they're on one side of the Earth. And so that may be even the major factor in explaining the wobble and the rotation axis of the Earth. And I don't think the wobble has anything to do with enhancing our capacity to live here. And it's a very tiny wobble.
Yeah.
But the fact is that it's a wobble that's been looking for a good answer. And now I think it's more than just the oblate feature of the Earth.
Yeah.
So it's more than just the Himalayan mountains. Himalayan mountains aren't going to do much, but these two blobs really would.
Yeah.
So I think that's fascinating in itself. And again, it's evidence that the more we learn about the past history of the Earth and its physics, the more evidence we see for a supernatural creator.
Yeah. Yeah, great stuff. That was a fascinating discovery. Thanks for sharing that, Hugh.
Oh, you're welcome.
Well, maybe I'll go ahead and talk a little bit about what I want to discuss. And I'm going to be looking at two papers published by the same research group within weeks of each other. This research team is at the University College Cork in Ireland, and it's very impressive work that they've done looking at not only evidence for soft tissue remnants in fossilized feathers that date maybe 120 to 130 million years in age, but they actually have worked out mechanistically how these materials undergo chemical alteration during the burial process and during the fossilization
You're
process.
talking feathers. So when you say soft tissue, are you talking the interior of the spine of the feather or the feather itself?
No, they're recovering molecular components that make up the feathers.
Got it.
So it's not like they're recovering intact feathers, but it's essentially the remnants of soft tissue materials, and specifically the molecular components. But feathers are actually quite beautiful features that are found on birds, but they also
and some people's hats.
Yeah, and some people's hats, thanks to the birds. And I think most people are aware that birds are the only major group of organisms today that have feathers.
Right.
That it's unique to birds. But feathers, are very important to bird biology. Not only, do they provide the means for birds to have flight, and feathers are this, these exquisitely designed, structures in terms of their aerodynamic properties. But feathers play other roles for birds. They repel water, they provide warmth for the birds, they form a type of armor protecting birds. They serve as a sunscreen, protecting the bird's skin, and they also are used to attract mates. So feather biology is really very important for birds, and part of what makes feathers so attractive to mates is the intense coloration, right? And this is due to pigments like porphyrins are responsible for the blues and the greens and the reds.
Color headquarters here, we got peacocks running around. So,
yeah.
Quite a display.
Yeah. Interestingly enough, there are carotenoids that actually are not produced by the birds but are consumed in their diets that give pinks and reds and yellows and oranges as well. And then there's also melanins. Eumelanin gives the black and the brown color, and then pheomelanin gives gray and a reddish color. So it's the combination of those pigments along with the physical properties that create iridescence that are responsible for the colorful display that you see in bird feathers. So there's a lot of interest in understanding the natural history of feathers. How did feathers come to appear on birds? What were the colors of the ancient, feathers found in ancient birds? That type of thing. What biological role would they play? And paleontologists now recognize that dinosaurs were feathered. In fact, there are two groups of dinosaurs, broadly speaking, the avian and the non-avian dinosaurs, and both appear to have feathers. But there's a lot of questions about what were those feathers like compared to the feathers that we see in modern birds.
And how many species of dinosaurs do they think have feathers on them?
I think the feeling is that it's quite ubiquitous, actually.
So more than just 10%.
Yeah, that it's a fairly definitive feature of dinosaurs. At least that's my understanding. I'm not a dinosaur paleontologist, so if somebody's watching in the show and they know that answer, they can
maybe
put
they
it in
can
the
put
comments.
in the notes what the percentage is. That'd be
Yeah.
fun to have.
Yeah. But, it's interesting because there are paleontologists today, a vast majority, who think that there is a deep connection between avian dinosaurs and modern birds. In fact, they would argue that dinosaurs never really went extinct. They live with us today. We just call them birds. So anyway, but there's a lot of interest in, again, the natural history of feathers because of its prominence in feather biology. And what is helpful towards that end are not only well-preserved feathers, but also the fact that there are now molecular fragments of the original feather material that can be recovered from feathers. Keratins can be recovered, and then melanins can be recovered. There's very good evidence that eumelanin was present and evidence for melanosomes, which are the organelles that harbor the melanin pigments. But there's a debate as to whether or not pheomelanin was present in these remains. And then with respect to keratin, the question is, what was the nature of that keratin? And so I'll unpack both of those controversies a bit. But here are just as a picture of the two papers that were published, one in Nature Ecology and Evolution and the other in Nature Communications. Very, very fine studies. But just to give people perspective, as we talk about what these researchers were doing, this is a cartoon showing on the left the structure of a feather, and then the feather consists of a shaft, which is the central feature, as well as these branches that come off of it. And then what gives the feather its volume in its body, if you will, are these barbules that are very small, thin structures that are networked together between the shafts. And if you look at a cross-section, you'll see that it's essentially made up of keratin, which is also the protein that is found in our fingernails and the scales of reptiles. It's
Scales of fish.
Scales of fish. It's found in our hair is made up of keratin. So it's a very widely dispersed protein.
So I can say I'm keratin deprived.
Yeah, you could say that. You could say that. But then you have these keratin proteins that make up the barbule, but then in the outer ring of that barbule are these melanosomes that are giving the pigmentation. Now, as I mentioned, one of the big questions is there evidence for pheomelanin in these pigments? And the reason why this is important to understand, is it eumelanin, is it pheomelanin, what is the combination, is that combination gives you a particular coloration. So if you're interested in what are the colors of the feathers, which is a clue to maybe...
Now, is it unique to feathers? Because keratin shows up in non-feather material.
Yes, yeah.
So it is unique to feathers?
No. Keratin is found, again...
What about the melanin, though?
Melanin is also
It's broadly
distributed as well in organisms. Yeah, we have melanin and melanosomes in our skin. Now, what's interesting is that one way in which you can determine if you have eumelanin and pheomelanin in fossil remains is to look for evidence for melanosomes, which people have discovered. And it turns out that the melanosomes that harbor eumelanin have a different morphology than those that harbor pheomelanin. And so this is showing 4 stages of melanosome development. And the eumelanin is harbored in melanosomes that are elongated in nature, where the melanin polymer or the eumelanin polymer is broadly distributed within that structure. The pheomelanin is spherical in shape, and as it develops, it's more of a clumpy distribution of the pheomelanin. And this is another cartoon showing how these melanosomes develop after they're produced in a structure called the Golgi apparatus. Now, this is a picture showing the molecular composition of eumelanin and pheomelanin. And what we want to take away from this is not only an appreciation for the chemical complexity and the chemical beauty of these materials, is that eumelanin is much less complex than pheomelanin, but that they are both heavily aromatic compounds, which is a type of bonding that is a highly stable bond. And they also are cross-linked structures, or they're made up of these repeating units that occur over and over and over again. But the idea that they're aromatic and they're cross-linked makes these highly durable chemical materials, which is why you would expect them to be able to survive for tens of millions, maybe even hundreds of millions of years, is that their chemical composition makes them incredibly durable materials. And so what this research team recognized is that, look, we can't directly detect evidence for eumelanin and pheomelanin because it's going to undergo chemical decomposition, but maybe we can detect evidence for the subunits or the chemical breakdown of the subunits. And so this next slide, we don't need to go into the details, just shows how they were reasoning from a chemical basis for what are the types of materials that likely would be left behind in fossilized feathers.
So these would be like decay products.
Right, decay products. So what they did is a very interesting set of experiments that involved taking black feathers, red feathers, and white feathers that have different compositions of the different types of melanins and the different types of melanosomes, and they basically heated them in dry aluminum foil at 200 degrees Celsius and 250 degrees Celsius to mimic the heating that would take place during the fossilization process. As those materials are under the pressure of the earth, they're going to heat, and that's going to lead to chemical breakdown. They also did an acid treatment as well. And what they ended up looking at were the distribution of the different chemical materials, the subunits as well as the breakdown products. So they were able to characterize how these things changed over time and what types of materials were present and what was the relative abundance of the different breakdown products. So this is a very sophisticated experiment that they're doing to get this understanding of not only the nature of the breakdown process, but then what would you expect to be left behind and the relative compositions of what you would expect to be left behind.
Now, the relative compositions, do they definitively identify these have to be from feathers?
Well,
Do they have that kind of data?
yes, because what they've done then is they actually have gone in and have done chemical extractions of fossilized feathers from 2 feathered dinosaurs that, again, would have dated 120 to about 130 million years in age. And they actually are looking at the different types of chemical materials that they can, when they do the extraction, they make the measurement with what's known as time of flight mass spectrometry, which is reasonably sensitive and can give you a good picture of the molecular composition of the melanins or the melanin breakdown products. And they could actually see evidence for both eumelanin and pheomelanin in this. So the argument is, look, by doing a much more detailed study, understanding the breakdown mechanisms and what are the materials that are going to be present, we can indirectly determine that there must have been pheomelanin present. And by looking at the ratios of the materials, you can now get a sense for what would have been the melanosome composition, what would have been the relative amounts of eumelanin and pheomelanin, which then can give insight into the coloration. And that's going to tell you perhaps how those feathers would have been utilized by these feathered dinosaurs, what their biological...
So they're not only able to use the ratios of these chemicals to determine, hey, this has to come from feathers, and not say from fish scales or scales of a reptile, but also the coloration of the feathers. Is that correct?
Yes.
Yeah.
And of course, I mean, what they're doing is you can do these experiments where you are extracting portions of the feathers, so you know that this is coming from the feathers themselves, right? So you can do that kind of...
Now, what's this frog-like creature there?
Well,
is that a
in the
control?
paper, they also were able to show that the fossilized remains of a frog dating about 10 million years in age. Also, they were able to recover evidence for both eumelanin and pheomelanin from the fossilized skin of this frog specimen.
So it's kind of like a control feature to...
Well, it's just additional evidence that that pheomelanin was preserved.
Yeah,
right.
Got it.
Right. So that's interesting. And for our purposes, what is impressive to me is we're moving beyond just simply, hey, we think we have evidence for melanin in feathers, to now we are understanding how the breakdown of those materials would take place during fossilization, and we're seeing patterns that are consistent with what we would expect to see. So this is now, you're taking the level of sophistication of the understanding of the soft tissue materials to the next level, because these researchers are now studying the process
I
of
understand how
taphonomy.
they're able to determine the coloration of the feather. Do they have enough data that they can determine, hey, these are feathers that were used to insulate the animal, or feathers to assist in mobility?
I don't think the data gives them
Not that much yet.
Okay. But it's part of the clue,
Okay.
the clues that would go together to determine how these feathers are being used.
Okay.
But even knowing how the feathers are used in modern birds, even if these dinosaurs were incapable of flight, they still could have functioned as a sunscreen, to repel water, to keep the dinosaurs warm.
Right.
So there's other functions, but again, understanding the coloration is an important piece of
that puzzle,
making sense of it. Now, in addition to discovering melanins, people have also discovered evidence for keratin in fossilized feathers, as well as in fossilized skin of ancient reptile remains. So this is nothing new, but what is interesting is, and we'll unpack this a bit, is what is the chemical structure of the keratin? Because in modern birds, the keratin is what's called beta keratin, and I'll explain what that means in a minute. But when they've studied keratin from the fossilized remains of feathers, it looks like it's alpha keratin. So the thought is, well, maybe the structure of the keratin was different, and that may have actually influenced the biology of the feathers, right? And that maybe because there's a different configuration for the keratin in modern birds that may tell us something about how the feathers were used. And so again, just going back to this diagram, a big proportion of the feathers is actually keratin. And to understand the structure of keratin, we need to do a quick review of protein secondary structure. These are the two most prominent secondary structural features you see in proteins, which have to do with the backbone configuration of the protein chains. Everybody is probably familiar with the alpha helix, but there's another structure that's an open extended structure called a beta pleated sheet, where it's a sheet-like structure that kind of has this up and down characteristic to it. And it turns out that alpha keratin exists as a alpha helix. So it's a long filamentous protein that's an alpha helix, and that these two alpha helices then intertwine around each other, and they have points of cross-linking, and then those alpha helices will intertwine around others to form a protofilament, and the protofilaments intertwine to produce protofibrils. Now, the reason why keratin survives is because it is this highly networked material, right, that's kind of knit together where there's heavy, extensive cross-linking, and that's going to lead to its survivability. And then this is showing a cross-section of a hair, and you can see how you have these remnants of cells that are just loaded with keratin fibrils.
So if you got wavy hair, you th more keratin than people who don't?
It has to do with the cross-linking of the keratin, actually. Because there's sulfur-containing amino acids that can form disulfide bridges. And so what you do when you, let's say you're going to someone's going to get a perm in their hair, you actually treat it to break apart the cross links, and then you introduce chemical, you set the hair the way you want it, then you reintroduce the cross links that stabilize that structure. So the chemistry of what you do to your hair when you get a perm is kind of interesting. Now, there's also an alternative form of keratin called beta keratin, and today I think it's referred to as the corneous beta protein, but it's essentially keratin, but it exists instead of in an alpha helical form in a beta pleated sheet form. And so then you can have these beta pleated sheets that form kind of a fibril structure, as you can see, and then you can combine them to create kind of a protofilament that then can interact with other protofilaments. So it's a fundamentally different molecular configuration. An interesting side note, when I was working at Procter & Gamble, we were interested in how our products were interacting with skin, and skin is loaded with keratin. And I could actually see an alpha to beta transition when we applied certain materials to the skin, and that actually correlated with skin irritation, believe it or not, because the transition from an alpha keratin to the beta keratin in the skin actually opened up what's called the transepidermal water barrier. And by losing that barrier, it allowed materials to enter into the skin that created irritation. So anyway, I actually have some direct experience doing the...
So were you working on that dandruff product that irritated your scalp a little bit?
Well, these are more skin products,
Okay.
but I won't tell you what they are to protect the innocent and the guilty too. But this is an image of, or photographs of the two feathered dinosaurs that they actually looked at. And they also ended up looking at something called the Green River feather, which is a 50 million year old fossilized feather as well. So these are the three specimens that they looked at. And what they did...
So the one on the right is not necessarily a dinosaur
No,
feather.
that's a bird feather.
That's a bird feather, yeah.
Right. And what they ended up doing is they used a technique known as infrared spectroscopy, where you can get the relative proportion of alpha and beta keratin. That's essentially what the technique is doing. But what they ended up seeing is that when you did a similar experiment to the earlier ones, where you heated the feathers in aluminum foil at 200 degrees, 250 degrees, or treated it with acid, what ends up happening is the beta keratin actually undergoes a chemical transformation into alpha keratin. And so when people are detecting evidence for alpha keratin now in fossilized feathers, they're arguing that is not actually the original configuration of keratin. It's actually beta keratin, and what we're seeing is actually the result of a chemical alteration. And so that means that probably the feather composition of dinosaurs was very similar to the feather composition of modern birds, that you're not seeing fundamentally different types of feathers is really the insight. So, this is, to me, science at its best. It's amazing to me that we're now beginning to understand what's happening to these molecules, and it's just creating an extra dimension of insight into the biology of past organisms, into their natural history. Now, as you well know, we've got friends who are young Earth creationists who are excited about these discoveries for other reasons, because they actually see the discovery of soft tissue materials in fossils as evidence that the Earth must be young.
That the fossils must be young, therefore the Earth is young.
Yes,
yeah.
Right. And the argument is kind of like this, that there's no way that you can actually have soft tissue materials surviving for thousands of years, let alone
hundreds of millions
of years.
Right.
Therefore, the radiometric dating used to determine the age of the fossils must be flawed. And the best way to understand the fossil record is that it's the result of a recent global flood catastrophe, right? And so I'll point out that there's absolutely no reason to think that radiometric dating is unreliable, which means there must be some explanation for how these materials survived for that period of time. And I wrote a book called Dinosaur Blood in the Age of the Earth to engage that question. And the reason why I did that is because this is becoming one of the most prominent arguments I see for a young Earth today.
Right. Yeah.
And the argument, again, at some level is compelling, because, well, how on earth could these soft tissue materials survive? We know all these decomposition mechanisms.
Well, like our soft tissue doesn't survive.
Right.
So
why would we think that this could survive for that period of time?
I get those questions several times per week on my social media, so this really is a big deal.
It is.
Yeah.
It is. And so that's why I wrote the book, Dinosaur Blood in the Age of the Earth, is to really give the argument a fair hearing.
Right.
And then to ask the question, is there any way to really explain mechanistically how these soft tissue materials survive? But again, the point that I want to make before I get into this is, and I'm not going to read this quote, but is that many times, sadly, young Earth creationists create the perception that what's being discovered, in this case, is intact melanin, intact pheomelanin, intact keratin. That's not what's being discovered. As these two papers clearly demonstrate, what's being discovered are products that have undergone chemical alteration.
Basically the decay products, same thing we see in radiometric dating.
Right.
Yeah.
And what we're seeing in the fossils is exactly what you'd expect to see, given the mechanisms that we're now beginning to understand.
And given the time duration that's consistent with radiometric dating.
Yes. Yeah. So, and then also, as I was pointing out, the materials that we're recovering are materials that are highly durable materials. Melanins are highly durable from a chemical standpoint. Keratins are. And in feathers, the feathers are basically keratin and melanins, right? And so the level of soft tissue material is very high in these structures. So the fact that we're seeing fragments or trace amounts of this material is not surprising, given the chemical composition of the feathers as well as the chemical durability of these materials. But in addition to that, there's another process at work, and that is there's a mineralization process. And once the minerals entomb the soft tissue materials, it's going to prevent them from breaking down further. It essentially protects them from, it either slows down the breakdown process or stops it in its entirety. And so you have these competing mechanisms. One is decomposition and the other is mineralization. And it turns out that we're discovering soft tissue materials in fossils that have been preserved under fairly stringent sets of conditions, where the fossils themselves are remarkably well preserved, which says it's in an environment that's conducive to the mineralization process outpacing the decomposition process. And we also are discovering that there's other chemical processes that protect or slow down the decomposition process that delays it long enough for mineralization to take place. So the bottom line is that there's nothing mysterious about the fossils or about the preservation of soft tissue materials. It all makes sense in terms of the chemical durability, in terms of the abundance of those materials in the original sample before death, that we've got mechanisms that we understand that are going to delay decomposition. We understand how mineral entombment plays a critical role in preserving these soft tissue materials. And we now have a good understanding of, at least for keratin and melanin, what kind of chemical changes are going to take place. And we see evidence that those changes indeed took place. So it's a very nice picture that's emerging.
Well, I think another compelling point is when you look at these decay products, they're showing up at the abundance levels you would expect given the dates. I mean, we do see that they are, you get less and less with respect to time.
Yes.
But you're getting less and less at exactly the rates you'd expect given the ages that are being measured.
Yes. Yeah. So the point is that this is really not something that should be used as evidence for a young Earth. In
fact, it's the reverse. It's evidence for an old Earth because we see the rate of decay at exactly the rate we would expect, given the age of life on planet Earth.
And it doesn't do any good to make really a flawed argument for the reliability of Scripture that isn't going to be accepted at all by the scientific community, that has no real scientific basis that undergirds it. It's one thing to challenge mainstream science, but that challenge should be a scientifically robust challenge, not a challenge that really is scientifically incredible.
If it's only being believed by young Earth creationists and no one else, then it gives you reason to say, hey, is this really credible?
Yeah.
It'd be one thing if they could cite non-Christian research scientists to say, hey, you got a case here.
Yeah.
But that's not in the literature.
Yeah, not even close to being in the literature.
Not even close, right?
Yeah. Okay, well, that's all I've got to share today.
That's great. No, that's very fascinating.
All right, so let's go ahead.
Hopefully people will get your book. I really love your book, Dinosaur Blood and the Age of the Earth.
Well, hopefully people get a copy of your book, Improbable Planet.
Okay.
Because that's a great way to learn about Earth design. All right, well, we'll go ahead and bring this episode to a close. Thank you so much for joining us. We would love to hear your comments and your thoughts about what we discussed. So please use the comment section to let us know what you think. And also make sure that you subscribe to our YouTube channel, Reasons to Believe 1. Use the notification button so you're alerted when the next episode of Star Cells and God drops. Don't forget to follow us on social media, RTB_official, and share this video with people who you think want to know more about the scientific case for the Christian faith. And remember that the more we know about science, the more we have reasons to believe.